Wendy Hartsock, science and peptide enthusiast. In this episode of Exploration Science, Dr. Michael Mina, the Chief Scientific Officer of eMed and former professor of epidemiology, immunology, and pathology at Harvard, talks about test to treat and the power of combining at-home test kits with telemedicine. He also dives into some of his work on using phage display to study immunology. Well, first off, I guess I should thank you for taking time out of your incredibly busy schedule to do this.
Oh, no problem at all. Happy to.
I appreciate it. Maybe I was thinking we could kind of start talking about where you are right now, like about eMed and about the company, and then I'll kind of backtrack to how you got there.
So in general, eMed is, I'm the Chief Science Officer at eMed, and we're a biotech diagnostics telehealth company. So essentially the goal of eMed is to link people to telehealth, but bring some of the tools that you'd expect from a regular medical visit really into the home by bringing the tools that you'd need or that you'd normally expect in a medical visit to telehealth. And so the way that it works is we generally create these telehealth kits, and they're a fusion of a diagnostic tool inside or a set of tools. And the kit is designed to sort of get rid of all the clutter of telehealth. Telehealth is oftentimes difficult for people to know, like your kid is sick. Do you go to this website or that website or another one? And what we're trying to do is kind of change how healthcare is practiced in the US with this idea of sort of urgent care, like first aid kits, but for telehealth. So essentially there's somebody might have a first aid kit and that will contain a UTI infection kit, a COVID flu infection kit, a sinus infection kit, a Lyme disease infection kit, et cetera. And those would be something that you keep in your medicine cabinet, just like you keep a first aid kit for when you actually need it. You don't want to have to run out to the store and get Band-Aids. It's very similar here. If you have a UTI, you want to just be able to pull this kit out of your medicine cabinet, and it will immediately connect you to a very focused telehealth visit with tests inside for UTI and physicians evaluating you in real time, sort of 24/7 on demand. And the other idea behind it is we know that things like scheduling and health insurance and finances are just obviously major barriers to people being able to make a medical appointment or feel comfortable going to see a physician, not necessarily knowing how much it's going to cost, or if they're uninsured, definitely not knowing how much it's going to cost. Mm-hmm. And this is an attempt to have you pay up front. So we never ask for an insurance card. We never ask for a credit card. Mm-hmm. Once you pay what's generally $25 for a telehealth kit, that's all you ever pay. And if you get treated, we even pay for the treatment and all of that would happen at the pharmacy. So we've tried to kind of streamline it in a way that people feel comfortable, saying, okay, I pay $25 for this UTI kit up front. And whenever in the next 2 years that I might have a UTI, I can pull that out and know that I'll be evaluated by a physician and get treatment at the pharmacy I desire, within hours without having to make an appointment with my primary care physician, or in most cases in America today, go to the emergency room or go to the urgent care clinic. So that's kind of the idea behind eMed, is to just rethink how medicine is brought to people.
I have to say it was definitely something. I can see the utility, as you mentioned, of it being so widely available that people don't have to make appointments, especially if you live in a rural area. But I also found it particularly helpful when I was traveling outside of the United States and we had the mandatory testing to get back in. It was nice to have that with on your person, so you didn't have to go find a pharmacy in another country. And
testing for travel was certainly how eMed actually started before the pandemic, but it pivoted. It saw that its platform, the platform that is eMed, which is armies of telehealth proctors and certified guides that can walk people through a test experience. That was actually what it got its start really working with Abbott, and in response to the pandemic, because there was this massive need to have some way of showing, hey, I was negative, I tested negative today. Most of the over-the-counter tests they can't verify that you actually tested or had given a result. And so there was this real need to kind of make it more scalable rather than having to go to the pharmacy or somebody in person and having them swab your nose and like sign off that you were negative. This was an approach to say, hey, we can actually do this. We can give people this opportunity to get a sign off, from home using this telehealth platform that we had set up and made it extremely, extremely scalable, especially at the peak of Omicron and things like that, doing 50 or 100,000 telehealth visits a day across the United States. And a lot of those people were actually using the test to get back into the United States or to get into other countries because they were all requiring this. And generally what we've heard from, millions of different customers is that it was kind of the easiest solution rather than having to be in Spain and trying to find some pharmacy to do a test that you can fly back to the US. It was like, hey, just bring this eMed test with you before you go abroad. And then you'll have it in your suitcase, for the morning of your flight back to the US, you'll be able to get a certified lab report. And it's actually a CLIA-waived lab report. Reports when you use it in the United States, I know it reports to all 50 states public health agencies. So it's also trying to keep, a lot of what I was focused on have been is how do we keep a lot of the public health infrastructure in place, even when people are using tests on their own. Oftentimes, especially in a pandemic, it's kind of like, do people get access to tests, or do public health agencies get data? Yeah. And, I don't think that those two should be in conflict, that we could give people access to tests on their terms at home, and we could get public health data to be highly accessible and even better quality data, delivered to public health agencies in real time. And that's a lot of what we focused on.
No, it's transformative in many ways. I think, data collection, but even like simple things like you don't have to leave the house and bring your infection outside of it. I mean, there's so many.
That's exactly right. It hasn't been announced yet, but my guess is by the time this goes live, it will be. But we were just selected as the NIH and the federal government digital test to treat partner. And so that's effectively, what we're doing is we're saying, hey, we don't want people who find out that they're positive on an over-the-counter rapid test to have to get on a bus and go into a clinic or a hospital and spread the virus just so that they can get treated for the virus, meanwhile putting other people at risk. And we're trying to bring all of that into the home. And that's what the administration is now trying to do with its sort of next phase of the pandemic test to treat programs, is digital test to treat at home. And now people can use, now people can essentially use, this is one example, COVID flu box, and you can test and, go all the way from just opening it up, working with the teleproctor, getting a clinic visit, and then even get the drugs delivered to your house if you have the Paxlovid or Tamiflu. And, it's not, in my view, it's not like a major leap in any sort of cool scientific way, but it's just how do we use the internet? How do we use the tools that have been developed over the last couple of decades that allow us to talk right now for healthcare? And why has healthcare been so left behind in this world that has just jumped and left forward in terms of web-based lives? It's time to at least let healthcare catch up a little bit,
Yeah, absolutely.
And make life easier for people.
Right. Yeah. And also, and it's not just the patients, right? It's the physicians and the nurses and the healthcare providers as well, where, instead of having to have a patient come in and you go through all the physical motions, that it must just streamline the process.
Yeah, it does. There's a lot of waste in the healthcare system today. A lot of, bloat due to just the way we triage patients or don't triage patients. The way that we have to bring people in and they fill out these clipboards, and there's just so much time and energy wasted in all of that, and especially for something like a UTI. Now, the average physician doesn't really want to see tons of patients with you. It's just not very interesting for physicians to see those patients, and frankly, it's something you could do almost entirely from home with a phone call. And, I think that there's a growing sense as physicians become more and more strained for time and overworked and burnt out. It's like, how do we kind of move things? It's sort of the next generation of, okay, in the clinics, it was a lot of what was on the doctors was moved to physicians assistants or nurse practitioners. How do I kind of take that same mindset and, even if still using MDs, make life easier in other technologically sort of savvy ways? And I think, or, using technology to make life easier for everyone involved. And we can massively drop costs. If you don't have to have, if you could pay $25 and have the entire telehealth visit plus the test plus treatment, that just demonstrates how efficient medicine, in my view, economically can be. We often don't have that kind of economic efficiency in the United States, but other countries have incentives to keep costs lower in medicine because they're generally nationalized healthcare systems. The US doesn't have that, which puts this massive strain on the whole system. And of course, that falls back on all of us as taxpayers and as citizens of the US to have this like enormous debt, and largely due to medical expenses. I think it's like a third of our GDP or something now, which is astounding.
Yeah, that's crazy. And I forgot to say congratulations, by the way, on becoming the digital partner with the NIH. That's actually like a really big deal. So congratulations.
Yeah, well, thank you. It's I'm very excited. We're just starting the pilot in December. We're going to be initiating pilots, so it's really pretty exciting.
That's great. So I want to talk more about your current role and what you do, because I think it's super interesting. But like I said before, I kind of wanted to jump back. You've done a lot of schooling. You did a lot of academic work as well as actually teaching. So maybe could you just start actually from like little tiny Michael, and is it Mina or Minna? Because I've heard it pronounced both ways.
Minna.
Little Michael Minna. Were you always kind of like a science nerd, or did you think, oh, I want to be a doctor? Like, how did it start? And then kind of what was your journey?
Well, when I was really little, I wanted to be a primatologist. That was like, Jane Goodall was my idol. Yeah. And I think probably a lot of people want to be primatologists. Well, I don't know if that's true, but I did. And so I guess I've always been a science nerd. I was always a good student and I always loved math and science. And I've always also been very much into artwork, and that's always been, I wouldn't say conflicting. And I think as I moved into sciences more rigorously, I found that science done the way that I like to do it really satisfies a lot of my artistic creative cravings. Whereas in high school, it's kind of hard to get those. You don't generally see science as creative in high school or in elementary school and such. But I found myself when I entered high school, I started getting very frustrated with the public school system and just kind of feeling like a cog in this big kind of school system. I grew up in upstate New York in a town called Saratoga, and it was a great town, good school system, but I was a little frustrated with it. So I decided to go to a Waldorf school for 9th and 10th grade. And they're schools that generally, they kind of teach you, they don't teach you to memorize stuff. They teach the foundations of a Waldorf education are kind of like, if you're going to learn physics, you don't learn Newton's laws and equations. You learn first about who was Newton and why did he even start doing his experiments? And you start developing knowledge, from the ground up rather than being kind of told to memorize things. Mm-hmm. And it was that experience that was almost one of the first kind of eye-opening things that made me realize, wow, science is not just a bunch of cool facts. I was always interested in the facts, but the actual scientific experiments and the root of why things are done, and why somebody would even start exploring something. That became just it really opened my eyes. And I have an identical twin brother who did not go to the Waldorf school, and it was kind of one of the first times we ever diverged in our thinking. Mm-hmm. And I started becoming really interested in the hows and whys. And I think both of us were always interested in the hows and whys, but it was more of it became my philosophy of how to learn and get through education and school was to really understand the root principles of things. And that kind of served me very well through really the rest of my scientific, endeavors in school. And then certainly up till today, just basically, really building the basic principles underlying it rather than trying to work on like not just kind of like half understanding based on memorizing equations or mathematics. It just took me on a different road in terms of how I started thinking about school in general, and made school really fun. I went to Dartmouth College. I was an engineer there. I was really focused on the one hand, biochemical engineering, on the other hand, public health and global health. And I halfway through engineering at Dartmouth, I ended up moving to Sri Lanka, where I was really interested in seeing how kind of healthcare and public health was being performed in very under-resourced countries. And before that, I'd already been going to places like Belarus and Ukraine and Nicaragua for different kind of experiences to see how kind of engineering and public health kind of fit together in different places. And I went to Sri Lanka, found a very interesting, had an interesting time in a medical clinic there. Mostly found that like healthcare, it can be extraordinarily abysmal in places, like reusing needles and things like that. When you just have very few resources. But I was also really interested in Buddhism for various reasons, and started meditating while I was there. It's a Buddhist country, which is part of the reason I was also in Sri Lanka. Ended up becoming a Buddhist monk, and spent quite a lot of time meditating until the tsunami happened, and that was 2004. The Indian Ocean tsunami hit. I then stopped being a monk and moved down and lived in a refugee camp on the coast for about 6 months, just trying to help out. I was pretty naive in 22 or something, and fairly naive to what was like actually needed in such destruction and devastation. Nevertheless, tried to raise a bunch of money from the US and tried to like live in this refugee camp and spend the money helping in a nearby city. But ultimately what living there did to me was it kind of set me off on this path of like really trying to use public health and engineering together. But also I realized I needed to learn medicine if I wanted to like actually understand how to be most impactful. And that was like, there were just a lot of things that happened in the camp. For example, we would get like large shipments of medical supplies or antibiotics and things that would be donated from China or Germany or the United States. And ultimately they'd be like shoved into a tent. And this refugee camp was just on the beach where a village, stood before the tsunami. And all these supplies had boiled. And it's just like people across the world were donating supplies that were desperately needed in this country and a lot of Southeast Asia at the time. But it's just like so clear there was this logistics breakdown, and just this like these like basic optimization strategies weren't being employed to sort of optimize the tsunami relief programs that were being set up around Southeast Asia at the time. And that was just such a pointed example of we get these medical supplies, antibiotics, and they just boil. Like what was even there was zero purpose. There were no doctors there to utilize them. So why have them sitting, like get them to the hospital? Don't just donate stuff to donate stuff. And so it was kind of that experience that for whatever reason, it just really made me much more interested. I kind of moved a little bit away from biochemical engineering, more towards like applying engineering principles to public health issues. And also decided to go to med school. But before that, I ended up moving to Nicaragua for a year or two. Just like I wasn't doing well, like going back to Dartmouth, like going from that tsunami refugee camp to being a college student at Dartmouth didn't make a lot of sense. It was like, what is like, how do you even like rejoin that kind of collegiate frat Greek system? I was never in frats or Greek systems, but how do you rejoin that world? And I had trouble with it. So I ended up applying for the fellowship from Dartmouth. So, it's given to a few students a year, and it's kind of for people who are particularly kind of creative and want to forge their own path instead of taking courses during a final year. Some people write books, some people do, many kind of PhD theses. In my case, I kind of went the research route and really spent the year just doing research in Nicaragua on trying to develop water filters for extremely rural areas. That required, it did require me to go back to biochemical engineering, and because I needed to like measure the efficacy of these like new water filters we were putting out in super rural areas. And to do that, you need incubators. But how do you have microbial incubators and set up microbial labs in a place with no electricity, which was like, I was on horseback. It was like a very rural part of the autonomous region of Nicaragua. And so I spent the first portion of that sort of senior year developing these little biochemical balls that have a very high specific heat, so they retain their temperature really well. But they're essentially plastic balls filled with a fatty acid wax kind of thing that when you boil them, they turn into a liquid inside the plastic shell, and then they phase change back to a solid at 37 degrees Celsius. If you keep them in a cooler, it takes for that kind of insulation, it took about 2 days for the balls to kind of like return back, all the while giving out 37 degree heat, which is enough time and stable temperature to grow up E. coli on petri dishes in a place with no electricity. And so I was able to kind of set up these little mini labs as I like took the tour around like Nicaragua, studying these water filters, trying to understand how communities use them. And one of the interesting things is that the more rural people who needed them the most, the water filters were actually damaging to health. They were getting so filled with bacteria that the pores would become themselves little, bacterial colonizers. And so it turned out like the basic finding through all of this year were the communities for whom these water filters were most needed were actually not benefiting from them. Diarrheal disease was actually going up in kids who had these water filters because pathogenic E. coli was like growing in them. And it was just kind of a bad system. But that led me to another, to say, well, if water filters don't work, what else could we do? So then I spent about the next 10 years on and off when I was in an MD PhD program, but kind of on the side, I ran a nonprofit in the same area of Nicaragua to teach communities how to make chlorine to purify their water using just like table salt and solar panels, and create these little micro businesses out in rural Nicaragua. And I would just go around and teach people how to make these generators, and they would have access to table salt from the market, and water and solar panels, and we could go through like basic electrolysis and create chlorine bleach. But then they could take a few drops and put it in their water, and that actually did purify their water. Well, it at least got rid of pathogenic bacteria and things. And so I ran that for a while I was in an MD PhD, and that kind of like has always been, that was a lot of like where I used my public health and engineering. And the more I started to get into medical school and PhD life, moved more in the direction of human health rather than just public health, kind of both sides, I suppose. Anyway, so that kind of like brings me all the way up to med school and PhD, and that was a kind of med school and PhD are what they were. I loved my PhD. I was at Emory, went there for CDC, which is across the street from Emory. Ended up getting into some research that was looking at potential adverse effects of flu vaccines in terms of increasing propensity for like live flu vaccines to increase propensity for bacterial co-infection and transmission of things like pneumococcus and pneumonia causing bacteria. CDC kind of understandably didn't want to actually have me doing that research in CDC's walls because it was a little too edgy and a little too ripe for causing a backlash against vaccines. So I ended up moving kind of all around. It was kind of a blessing in disguise. I just got to select some of the best labs around the world at St. Jude Children's Hospital in South Africa, at Princeton. And I just kind of finished did my whole PhD in all these different labs. It was very independent. And that kind of set me up for success, in terms of, I just was able to, be in truly the top, laboratories around the world. Because I wasn't stuck to just one PhD lab at CDC. Right. I could kind of pick and choose, and I was lucky enough to get funding for my PhD through a fellowship, and then ended up doing postdocs at Princeton and then Harvard, finished medical school, went back to Harvard for residency in clinical pathology, laboratory diagnostic medicine, and then became a professor in epidemiology and immunology at Harvard, and also a professor at the medical school in pathology. And And then pandemic hit. It's a different story, I guess, of the last 2 years and 2.5 years. And ultimately, it kind of pushed me out of being a professor because I found that, while I was arguably very successful, as a professor in publishing, developing new biotech tools in that space, I found my real calling during the pandemic was trying to advocate for people and bring them, push the government to make the right decisions to get people the tools they needed in this pandemic. And that was largely where I found most of my energy, was advising the president's team, advising governments around the world, trying to teach the public about public health, whether it was on CNN or the New York Times, and then really advocating for simple tools like rapid antigen tests. And at the time when the pandemic hit, the FDA was very against humans or Americans having access to rapid antigen tests. We have a very paternalistic healthcare system in the US, and it was not considered kind of appropriate for Americans to have access to know if they have COVID without a physician in the middle, which I don't really agree with. And so I just found myself really advocating and, doing a lot of research. My lab was extremely productive to try to form insights around the pandemic. But ultimately I decided to just kind of remove myself from Harvard and enter industry more, because it's where I think, what I do today is actually able to touch millions of people in their homes, really bring access to healthcare to them in a way that writing papers for Science and Nature just wasn't really doing for me in many ways.
And I do want to talk about your research, but I also, thinking about what you were mentioning of sort of communicating science to just a huge spectrum of people, right? When you're in public communication, you've got people from so many different levels and backgrounds that you have to message to. So what have you learned about public communication that would be totally different than what you would do if in a classroom at Harvard?
Yeah, well, I've always loved teaching people across a whole spectrum of educational levels. So way before the pandemic, even when I was still just starting medical school, I started teaching courses about vaccines and sort of basic cell biology to alternative healthcare practitioners and craniosacral therapists and massage therapists and chiropractors, people who generally don't understand the molecular building blocks of the world, and how the world is really shaped from a molecular perspective, but spend their whole days touching humans and manipulating the tissues that are made up of all these building blocks. And so, I've just always tried to give workshops and teach and give lectures to people from, at every educational level, from people who have zero biology experience up to postdoc PhD students and such. And when the pandemic hit, that voice or the need was certainly amplified a lot. But I think one of the reasons I became a pretty kind of vocal or known voice that was interviewed by the media a lot, or was on the news a lot during the pandemic was, I would love to be able to say it's because I'm so brilliant or something, but I don't think it's that at all. It was that I do think something I've worked on very hard for many years is how to know who you're talking to. And in the case of being on CNN, you're talking to everyone. You're not talking to any specific person. The people you're talking to have no idea about any of this stuff, with viruses and immunology and vaccines. And I've really loved talking, being able to gauge the words that are coming out of my mouth based on who I think the audience is, and using different analogies. When I'm teaching postdocs, I use a lot, many fewer analogies. When I'm teaching high school students, and I taught high school students in the summers at this college camp that I used to run for science, and I love teaching them because I would get to use all these different analogies to get these students who really haven't taken cell biology in any real hard way, but are in 10th grade or something, or 11th grade and getting ready for college, be able to, or they hadn't taken things like immunology, I should say. A lot of them had taken cell biology, to get them to understand this extraordinarily complex world of the immune system and molecules and some of the tools that we would use to probe the immune system. It really takes, how do you do that in 2 weeks? Get somebody who really has no idea what the heck you're talking about, to get them able to do little experiments and understand a bit about, the complexities of cytokines and interleukins and phage display and stuff. And I just really, really enjoy that approach to talking to audiences. And the hardest thing for me is in the pandemic, it became so charged that, a lot of scientists and a lot of doctors, frankly, don't know how to talk to the average populace. And sometimes when you're talking to Americans who don't have any experience, you can't be completely accurate scientifically. You have to use analogies that kind of cover enough so that it gets people to understand generally what you're talking about, even if sometimes there are subtle scientific inaccuracies. It's worth it if you can get people to understand 85% versus if you're totally accurate, maybe they'll only understand 5%.
Yeah.
And it was a real challenge because things got so charged and heated in this pandemic with, every time I would tweet or be on CNN saying one thing, I would get a barrage of scientists and colleagues saying how could you say that? That's not accurate. It's well, if I gave the words that you want me to use, the right scientific words, nobody would have any idea what I'm talking about, and I would have no voice because CNN would never have me back on to talk about it. And that was a real challenge, I think, was where kind of the heat and tension of the pandemic across scientists actually became the more challenging thing rather than talking to the public.
Right. And I think maybe just a point to make is that when you say not accurate, it's still the outcome is true of what your analogy is. But you're not using exactly the same scientific lingo
that's what I mean by it.
Yeah,
exactly. You might say B cells producing antibodies. Technically plasma cells produce the majority of plasmablasts produce the majority of the antibodies that are secreted, but people don't if I try to teach people about plasma cells on CNN, they'd never get it. But at some point in the pandemic, everyone started hearing the words B cells and T cells. And you can start saying B cells produce antibodies. They don't really secrete antibodies, so they're not the ones you're measuring in your blood, but they are the precursors to the plasmablasts and things like that, where you'd have the staunchy immunologist saying, "Oh, that wasn't accurate," or you'd have somebody else. And now actually the most difficult thing today is a little bit less about that, but it's more we've become really divided in terms of feelings about what precautions Americans should be taking today, or people around the world should be taking. And, now I view the real challenge is I've always wanted to have somewhat of a more measured kind of balanced response to this pandemic. Locking down to me wasn't necessary if we gave people the right tools to know if they were infectious before they went to work. Did we ever have to lock down? Things at this point, does everyone have to wear masks 24 hours a day? I think pretty much the populace has spoken. The answer to that is no. But if I come out and say that publicly, it creates a barrage of tension, and it's really balancing these pieces and the zero COVID folks with the long COVID folks with, everyone has their piece, and all of it's really important. But there's always going to be people who are very unhappy in today's sort of where we are with this pandemic. Is we're in this transition phase, and now that's become the most difficult piece, is how do you message that, that people who are susceptible should definitely be getting boosters. But if you're 30 years old and you've been infected twice and vaccinated 3 times, maybe you don't need a booster right now. Maybe you're not going to benefit very much from it. How do you say that without 1 million people literally freaking out on you? And that to me is a craft and an art, and I don't know that I do it well, but it's become the more challenging piece of public communication today.
Well, and I think even you can deliver something quite well, but when someone puts subjectivity on something that should be objective, no matter how you say it, because they're listening to it with that perception, with that, preconception rather. So
That's
yeah,
exactly a great way to put it. Yep.
humans.
I was shocked.
Yeah, exactly. So I did want to talk about some of your research as well of sort of what you're doing. Can you just give me like a general outline, and then maybe we can dive into a couple of other projects?
Sure. So my research, before coming to eMed, at eMed, I'm doing certain types of research. And I'm like, I can't help myself. I had to get like NIH grant to brought NIH research into eMed. But the more exciting research, I think, is really what I was doing before eMed, and I certainly want to, get back to at some point, which was to develop the tools and the systems that kind of combine mathematics, epidemiology, and immunology with new biotech molecular tools that would probe people's immune responses in very, very high resolution, and ideally use it for all sorts of things. But what I was most focused on is how do we profile and probe people's immune responses across, for evidence of exposure to practically any virus or pathogen that could impact humans, and then make that so scalable that we could do it across populations and ultimately create what I think of as a weather system for pathogens, a weather system for viruses that I call the Global Immunological Observatory, and or GEO. And the Immune Observatory is this idea that just like we have sensors out in the world, we have weather balloons and weather buoys and thermometers and things capturing barometric pressure and wind and temperature all around the world, so that frankly, like you or I could just go onto our phones or our computers right now, and we could actually know what is like the detailed weather today and prediction in some, random community in Uganda. Like, it's amazing that we can do that. And this whole idea of developing the weather system led to just a massive ecosystem of new innovations around forecasting, around mathematical models, around the requirements for computational power in these systems. And I view the weather system as like this amazing science that really pushed forward our need and sort of the mathematical disciplines that allow forecasting to happen. And a lot of those, like I think we can do the same thing with pathogens, where rather than you needing to go and get a test when you're wondering why your nose is runny or your child's nose is runny, could you open up your phone and it says, oh, there's like, high adenovirus in your community today that we know from passive surveillance of profiling the immunological repertoire of random blood samples that are coming from, hospital labs that are, just from random patients that might be in a hospital for any number of things. But if we could use their samples as kind of anonymous buoys, where we're not getting any personal information from the sample, but we might be pooling samples and looking at what is the antibody repertoire in these samples over time. And if 1 month you start to see, antibody levels and diversity of antibodies for adenoviruses are starting to increase across the country, well, that probably means that for the next few weeks, at least, you're going to be at, in those communities where you see it, there's going to be a lot of adenovirus. And if you can say, and there's nothing else going, then probably if you open your phone and you ask, why does my child have a runny nose? And you're in one of those cities with a lot of adenovirus evidence from these kind of weather buoys, you'd be able to infer computationally and statistically that, hey, my child probably has adenovirus. Maybe it's not the end of the world for them to go to school. But if you see that, hey, RSV antibodies are really picking up, maybe you don't want them to go see grandma. Yeah. And so I think we can do that. And I really believe like the technology that we were building is based around phage display. And it's really highly, highly scalable and cost-effective ways to make epitope displays. And we can have phage displaying across the library of phage. We can have encompassed across that library is sort of the epitopes that represent the full proteomes of practically all viruses that might impact humans. And we can use those to capture antibodies that are in a drop of blood or a drop of saliva. So however you want to capture blood or saliva, it could be through passive acquisition of samples before they get thrown away in a hospital lab. It might be from blood donors or plasma donors. It might be from active surveillance, where you're actually going on after people to give a finger prick. All different ways that we could capture people's like biosamples passively, ideally. We could then be processing them through these epitope displays. Each time a sample gets presented to this epitope phage display, you can then pull down any of the phage that have antibodies stuck to them. And then you sequence those phage and understand, oh, this particular sample had a whole lot of very high levels of adenovirus antibodies or influenza antibodies, and not many RSV antibodies. And
Right.
And if you do that at a population level or even longitudinally across people, you can actually start to see the front of a wave of an outbreak and the front of a wave of new pandemics, and even novel viruses you've never known about have a signature that can be detectable from these types of displays. And to me, that's one of the most powerful tools not yet utilized in public health forecasting is just this idea of massively multiplexing. Hundreds of thousands of distinct antibodies can be captured from a single person in a single sample. And very reliably, if I took a sample from you today and tomorrow, I'd have almost identical antibody signatures, despite just it being 0.2 microliters. So every 0.2 microliters has almost a full representation of our circulating antibodies, which is just astounding when you think about it, like how packed our blood is with these little molecules. And it also allows us to do really interesting things. Like if I am taking anonymous blood donor samples and I'm creating this kind of immune surveillance program to understand the landscape of infectious disease in the population, I could be collecting just random samples. I have no idea who the samples are from, but I could be running computational algorithms on the repertoires that come from each sample. And if I have a sample from you, I might not know anything about you or who you are or where you live. Maybe I know your zip code, or something like that, just to have it be good for public health. And I know the day that it was taken. I might have a big database of these repertoires, and then, I might find one today, and I can run and challenge that repertoire computationally against all the database that we have. And I can say, oh, this same person or this same repertoire was in my data set 6 months ago. And just computationally from how stable the repertoire is, it tells me no idea about who you are in particular, but I can link the two samples to say these came from the same person, very much like genetics would do, only in a more random way or more kind of discrete way in this case. Or
you can't backtrack who that's
exactly.
Like, it's not the code for the person.
That's exactly right. It's a de-identified. It's really de-identified or unidentifiable linkage. And the nice thing is when you do that across people, I would be able to say, okay, this person was here 6 months ago and this person's here today. And in the meantime, they had a new spike of some antibody against some new coronavirus. And that would tell me like, oh, well, there was clearly somewhere in the last 6 months, this person got infected. And if I do that across thousands of people, then it narrows the window of where those spikes are happening to a very clear timeline. And that allows you to get to the front wave of an outbreak without ever having to know, anyone who you're getting the samples from, maybe, basic demographics, depending on how kind of like resolved you want the data to be. But in general, there's ways to do this where you don't have to know anything about the people, but you can actually link their databases, their samples together, and almost create longitudinal cohorts that I call digital longitudinal cohorts because they're constructed purely computationally from the immune repertoire. And the technology that we've been working on, which we call imprint. And it's that you have, just like you have a fingerprint, which I could have your fingerprint, but if you're not in any database, I have no idea that it's from you. But, just like we have a fingerprint, our immune system is a fingerprint, and it's highly, highly stable over decades, in fact. So I could take a blood sample from you today and a blood sample in 20 years. And until you get much older so that your immune system starts to deteriorate, or you have cancer and you go on chemo or something, in general, it stays so stable that I could like imprint you and I could say, hey, these two repertoires came from the same sample, even 2 decades apart. Like a personalized barcode you have in your immune response.
That's crazy and awesome.
I agree.
I mean, I guess the implications, it really does depend, like you said, on how you were to implement it, because it could be something like the pollen report, right? So do I send my kids with masks today to school, or do I keep them home, or they just go freely? Like, I mean, that's
it's just like you get a weather report and it says, hey, it might rain today, or it's
right.
like cloudy and you're looking at the sky, you're like, oh, I'm going to bring an umbrella just in case. Right. Then in this case, it's like, hey, we're in this period of time when there's like clearly a lot of, adenovirus, which you don't usually test for, but hey, you know what? Maybe you don't want your kid to get adenovirus. Maybe you send them to school with a mask on or during flu season. Yeah. There's no reason why we have to use hospitalizations to get this data, which just show us they're generally a lagging indicator. And usually it kind of takes us a while to realize, oh, shoot, we're in a flu outbreak. Right. And it takes people off guard. And if we do this across just an amazing array of different viruses, we will learn so much. We barely know how viruses transmit or pathogens transmit, like we think we know. But the reality is that COVID has told us, like, we don't know the rules of the road we know some things. And if we start measuring this at scale, we will learn so much over the coming 10, 20 years about how pathogens transmit that will give us much, much better indications of how to then limit that transmission, how to keep the most vulnerable healthy, while also keeping a healthy amount of transmission so that kids can actually build up immunity. Mm-hmm. And so, like, we don't want to, unless we're really aiming to eradicate a virus, we don't want to have people go too long without building up immunity, because then we have things like SARS-CoV-2, which is like adults get really sick mm-hmm. because they've never seen this virus before. That wasn't because we kind of avoided it, because it didn't exist. But, there's a reason why kids don't get that sick from SARS-CoV-2. It's because, like, humans are evolved to see pathogens like this as babies, when our tissue turnover is really fast, when our tolerance to pathogens is really high. And then the idea is you do all this like hard lifting, heavy lifting early on in life to build up your immune system. And we used to use the same technology as phage display to follow kids in their first like 15 years of life, but specifically really in the first few years, we'd get a lot of samples from the same kid mm-hmm. and watch them in these longitudinal birth cohorts as their immune repertoire kind of grew and developed. And it's like amazing to see how early children start getting exposed to coronaviruses or rhinoviruses. First 2-3 weeks of life, kids are starting to build their own new repertoire. Mm-hmm. And that's generally why by the time we're adults, rhinoviruses and adenoviruses and seasonal coronaviruses don't bother us, is because we've seen them 100 times. We have like so much immunological memory and knowledge how to fight it off that by the time we're adults and our tissue doesn't regenerate quite as well and we're more susceptible, like, okay, we have like a better set of tools. SARS-CoV-2 comes around and it's hitting babies. They're probably generally babies that are responding to SARS-CoV-2 very similar to how they would seasonal coronaviruses. But it's the adults who are like really taken off guard because our bodies have not been evolved to see a virus for the very first time. And so it's pretty cool to use these technologies. There was a whole other area outside of like as public healthy stuff. It was more understanding how the immune system evolved and then erodes again throughout a whole lifetime from like 0 to 100. And really understanding what influences somebody's immune age using these tools. Can we understand, are there certain factors that maybe make a 50-year-old by sort of annual age? Some 50-year-olds might look like a 30-year-olds from an immunological age, and some 50-year-olds might look like a 75-year-old from an immunological age, how diverse and robust their immune system is. And we were really trying to explore that a bit, like how do people's immune systems evolve and develop, and where are there gene by immunity interactions happening there that would influence it, and like that.
Wow. I have so many questions and so little time. So you might have to do a part 2. But Something I think just to maybe go back on that you brought up of like not living in this sanitary society where we're bathing in hand sanitizer and spraying everything down with Clorox, and how important it is to actually get exposed.
So I think, this gets to this, what's called the hygiene hypothesis. And, do people potentially who don't get exposed to normal microbial flora and viral pathogens early in life, are they more susceptible to asthma or to allergies later on because their immune system kind of goes a little haywire? And we started studying this exact question. We had these birth cohorts of children who were genetically quite similar, and they were I'm like blanking. I think they were Finland, Russian, and Estonian, all at a point where those three countries meet. Pretty sure it's Finland, where the three countries meet, and they have very similar genetics, but totally different socioeconomic backgrounds and propensity to like be exposed to pathogens as kids. And the reason was there were all these Finnish kids who were, or maybe it's Denmark. Anyway, I have to look it up.
We'll put it in
yeah, that's right. Geography 101.
Yeah. I mean, you're a fellow geographical sufferer as far as like where things, anyway.
But in any case, we looked at these children. There was in the children who were the highest income and had the least kind of exposures as children, there was this really high risk of children becoming type 1 diabetic, like around 5 or 8 or 10 years of life, and getting type 1 diabetes. And so the question was like, is this related to immunity? What's going on? Why is the rate of type 1 diabetes in this childhood cohort so high? And what we found was something that I just think is astounding. As I looked at the immunological profiles of these children and how kids sort of develop their immune repertoires, it was the children. I figured the children who came from kind of the most pathogenic or sort of the most exposed regions would have like crazy immune responses and just like tons and tons of immunity. But it turned out when they got things like a measles vaccine, which I like to use measles as a control because it's something they generally hadn't seen in real, like out in the regular natural world, they only saw measles epitopes through the vaccine, which is the whole live virus vaccine. What I found with measles rubella, as an example, is when the children from the higher income country ended up getting an MMR vaccine, their immune system would go crazy. They would develop antibodies to so many different epitopes across the measles virus. Whereas the children from Estonia and Russia, who are generally lower socioeconomic status, relatively speaking, and were generally more exposed to pathogens as babies, when they got an MMR vaccine, they would have much more sort of nuanced, controlled immune responses to it. And they would generally have responses that, somehow, I don't know that we never got to the mechanism. We're still studying it, really keyed in on just the particular epitopes that were going to be most protective. Whereas the kids in Denmark, essentially had, or Finland, I need to remember, the higher income nation kids had just these massively kind of out of whack responses, as though their immune system didn't learn kind of to sort of have checks and balances.
Right.
And so what we think is that these kids kind of like the natural evolution of humans is to be exposed to all these things like when we're babies. And if we're not, like it might be some tolerance issue or our immune systems don't fully learn to kind of like not go haywire when they see something new. And that might be what's responsible for increased allergies, which are immune mediated in certain ways, increased autoimmune disease, which are definitely immune. Obviously, they're autoimmune, and it's almost like the immune system doesn't know how to check itself and bring it back down after it got exposed in these kids who didn't have a lot of exposures previously. And it was just a really amazing set of research and data that was developed using these phage display epitope displays that I certainly want to get back to, because I think it just has these profound. There's not a lot of people using these technologies in the world to study the immune repertoire. And even fewer thinking about using it for longitudinal studies to understand the development and demise of immunity or things like that. And so I really want to get back to it, for both public health and basic human immunology. Most of these technologies are used currently for like drug discovery and things like that, which are equally as important, but just a whole different, I love that there was like this fusion of biotech meets public health meets human immunology in a way that generally these technologies, like those worlds don't always collide in that kind of way.
And then throw in data science, and there you go.
Exactly. And you have to throw in data science because it's massive data sets. And, and I love data science. So half of the lab was really more in the mathematics and half the lab was in the biotech, development space. And the whole lab was in the, let's combine these space. It was really fun.
Okay, I could talk to you all day, but you probably have another meeting. I probably have to let you go. But let me just start by thanking you again for your time. This is super fascinating. Like I had so many more questions I want to ask.
Well, always happy to talk, and thanks for having me on. This was a lot of fun.
Thanks for tuning in to this episode of Exploration Science. As always, we welcome your feedback and suggestions for topics that you'd like to see covered. You can leave those suggestions in the comments below or tag us on LinkedIn. You can also find this podcast available as a YouTube series by searching Exploration Science. Thanks again for tuning in.